Okay guys, so we continue to question 2.4. So in this case, let you remember that we have a capacitor and we have a battery. This is the capacitor plate on top of each other, and the area of each one of them is A. Okay, A is the area and the voltage is V0. And apparently this capacitor is not strong enough. It's not holding enough energy. Capacitor coming from the word capacity. The capacity for energy is low. So instead of buying a new capacitor and do other stuff, somebody suggested instead of using the old capacitor that we have, we can shove in, here it is, push inside a conductive block. Here, we push it here inside the capacitor. But when we do this, we first of all open the circuit. Okay? So here accumulate some charge, the initial charge that we calculated in the previous section. And here is the same, here's the same but opposite charge, because if here there's electron, right? So the electron here would want to go away and leave a positive charge behind, because at the beginning everything were neutral. Okay, so we want to push this conductive block, here it is, and the size of the conductive block is A, this is the area, and its height is L. So the volume is A multiplied by A. This is the volume, and we push it. Okay, so what is the idea of this? The idea of this, that I open it, is that I have some initial charge, but when I'm gonna close it, I'm gonna stay with the same charge. QF, we're gonna talk about that, but this is the idea why I open this thing up. And my question to you is, how look the electric field in space? So I want to ask you, what is E right now? Okay, so we can, instead of have this three-dimensional drawing, we can do it in a simple way, which is just to draw the circuit. So how does the circuit look like? The circuit look like this. We have a battery, right? And we have the first plate of a capacitor, right? And here we have the plate of the capacitor, and now I want to draw this. But I want you to notice something really interesting. If I have here a negative charge, right? A negative charge, and this is a conductor. This is a conductor, right? So you conduct electrons. So the electron here gonna feel this and would want to go away from the charge that they sense here, right? Due to the screening effect of them. And you're gonna leave here a positive charge. This is negative, because we're gonna leave here positive charge, but on the top of the surface, negative charge, and the negative charge will want to go away and leave behind what? A positive charge. So what actually happened, this is right now, let's draw them. This right now is a positive, right? This one is negative. And here I can actually draw my conductor. Let's do the conductor in purple, so you can notice between them. So here, this is the upper part of the conductor, have some negative charge, right? And here, I have the other part, which have positive charge. So you see this? And we can sign the distance between each one, right? We can say that the distance here, right, from this capacitor to this capacitor, we can call it D1, and declare that this is a Z-axis, right? This is Z, and this is the 0, right? And this, the end of it here, gonna be D. Good, and this here gonna be, we're gonna call it D2. This height. Okay, this is D1, D1, D2, and D2 minus D1 is L, right? The length of this block. And the sign is not that good, because we decided here, now it makes sense. D2, and this is L. Okay, so right now we can write what is the electric field. So the electric field everywhere in space is equal to, when we are above D2, right, we have here two capacitor plates, right? This is this area. So in this area we have minus Q over A epsilon 0 at the Z direction. Why in the Z direction? Because the electric field the minus Z direction going down. Okay, and if you ask yourself, and you should ask yourself, hey, where this is coming from? So remember that I told you that we have sigma charge density. Remember when we calculate the electric field inside the capacitor? So if sigma is constant, we can say that sigma is actually equal to what? To the total charge over the area itself. So this is another way to write it. It's important for you to know that way. So I can write immediately this term. And let's continue. So that's what you have here. Inside and this where this is happening. Where location this is the electric field. This is the electric field if Z is larger than D2. Which means we are here. Larger than D2, we're between this part. Okay? So let's talk what happened when we are inside this capacitor, the lower one. So the lower one we have minus Q A Z. So it's the same thing. Why minus? Okay. Why it's minus? Because the same thing here, right? The test charge is actually repelled where? Downstairs. So down in Z. So it should have a minus. We already know the size. We use Gauss' law to calculate it. And this is in Z direction. And where this is happening? It's happening if Z is between 0 to D1 until this conductor that we push inside. And what is the electric field inside the conductor? You should know it. 0. Inside the conductor, the electric field is 0. You learn about this in the lecture. So this is 0. And where this is inside the conductor, between D1 and D2. Okay? So this is the electric field. It's actually a vector. So I add here a line. And we solve 2.4. We found what is the electric field all over the space. And we noticed that when we push inside a conductive block, we actually got this capacitor split into two capacitors. You see it? These two and these two, which are connected in series. You see it? They're connected in series in the circuit. That's what happens when you push it. Perfect. Let's move on to the next question.